Now we have discussed about one fluid property which is pressure. Whenever we are talking about effects of compressibility, there are other related fluid properties which come into the picture in a very related manner, and those properties we will look into one by one briefly. So one of the important properties will be density. So loosely what we say, that if we have a volume, elemental volume, say delta V, we have the mass of the molecules which are there in this delta V. So we take mass per unit volume. All of us like to write limits, so we will write limit this as delta V tends to 0. We will think that nicely it should give a limiting definition of what is the so called density. Mathematically very nice, we will see whether it works or not. So what it says? It says in the limit as delta V tends to 0, that means limitingly small volume, you find out what is the mass of molecules inside. So you find that mass per unit volume to get local density at a point. That is what this definition is saying. Whether it works or not, we have to come back to the continuum hypothesis to adjudge. So if we remember that in the continuum hypothesis we disregard the molecular nature and we just consider that it is a continuous medium. Does not mean that there are no molecules, but obviously we are abstracted of the molecules and we are just representing their gross effect. But whenever there are molecules, we have to see that what is the number of molecules within this elemental volume. Again, if the number of molecules within this elemental volume is very small, then because of the statistical fluctuations, even uncertainty in one molecule will give a lot of error and will give a lot of fluctuation. So it is critical that what is that elemental volume that you should choose, it cannot be too small. What is the smallness? The smallness will come with a length scale. The smallness of the length scale here is the mean free path lambda. So a very small volume when we say, then that will scale with say lambda cube. Lambda is like a length scale which will correspond to a very small volume. So when the volume is of the order of lambda cube, elemental volume, then it will have lots of uncertainties in the statistical fluctuations of the molecules, because within that length scale you really have uncertainties related to collision. On the other hand, if you take this volume delta V very large, then also we can calculate a density, but it will not be able to capture the local variations, it will give a global average. Therefore one has to choose a threshold length scale for calculating this density, and how it should be sensitive to the length scale. If you make a plot of say the length scale that you choose, say we call it LS, and the density that you predict. So you will see that if you choose a very small length scale, you will get a variation, this type of fluctuation, then it will come to a steady one, and then if you choose a larger length scale, it will be changing like this. So what is the significance of such a plot? These length scales are small enough so that you have really random fluctuations because of the uncertainties. This length scale is fine. Beyond this length scale you have a variation. This variation is because over the system length scale the density is varying from one point to the other. So a correct choice of length scale may be something which can be say in between these two. So in between these two limits. Therefore if we say delta V tends to 0, that is not fundamentally correct, because delta V tends to 0 may make you fall on this regime, because delta V tends to 0 means mathematically delta V is as small as possible. So as small as possible will obviously be something smaller than as big as possible. So obviously in that context one has to remember that this delta V tends to 0 should be corrected, and how it should be corrected? We should change it as not delta V tends to 0, but delta V tends to some delta V star, which is like, if we call this as LS star, then maybe it is of the order of LS star cube. So it is a threshold length scale beyond which you are not having such uncertainties and fluctuations affecting your density calculation. So this delta V star, therefore we can say, is the smallest elemental volume over which continuum hypothesis is valid. So it is not tending to 0, but tending to a limitingly small volume delta V star over which still continuum hypothesis works. Below this limit continuum hypothesis might not work, and therefore this definition will not work, because this definition is on the basis of a continuum description of fluid properties like density. So we have talked about density, we have talked about pressure. Next let us talk about bulk modulus. So all of you are aware of the basic concept of bulk modulus, but let us just see that how you have defined it. Let us try to define it first in a very loose manner. It is always important to get a qualitative feel, and then of course you can have more sophisticated definitions. We will not go into very detailed sophisticated definition of bulk modulus, because it requires a detailed understanding of thermodynamic processes, and therefore we are not going into that type of definition. So in a loose sense, if you are applying say a pressure differential delta P that is expected to give rise to a change in volume of a fluid element, let us say that change in volume is delta V. So original volume was V, so this is the rate of, or this is the total change in volume per unit volume. So this is a kind of a volumetric strain, and this is the pressure differential which is responsible for the volumetric strain, and you expect that if delta P is positive, delta V is negative, because if you press a fluid element it should compress, its volume should decrease. If you want to give the corresponding fluid property a positive number definition, then you should adjust it with a negative sign. Now you can relate the change in volume with the change in density. How is it possible to relate the change in volume with the change in density? So you have say consider the mass of a fluid element. So that is the density into volume. From now onwards, whenever we will be discussing about the volume, we will be using a symbol not V but V with a strike through, because we will be using V for velocity also. So just to avoid that confusion between the symbol of velocity and symbol for volume, we will be just distinguishing those in this way. So I will not be repeating the symbol many times, but once I will be using this type of symbol, you just take it that we are talking about the volume, not the velocity. So if you want to say see that what is the relationship between the elemental change of density with the elemental change of volume, what you can do simply just you can take log of both sides and differentiate. So if you differentiate keeping in mind that the mass of the fluid element is conserved, so its derivative should be 0. Therefore loosely, like if you are following this definition, we can relate delta V by V with delta rho by rho. So that will just absorb the minus sign and it will be like this. So it is like rho delta P over delta rho like this. Now we can relate delta P with the velocity of flow. In a order of magnitude sense, the delta P and the velocity of flow, this is just like if you consider that there is an equivalent pressure change which is brought about by the change in kinetic energy of a fluid which is moving with a velocity u, then this is not that they are exactly equal, it is just to say that one scales with the other in this way. So you can therefore write a scale of k as, so rho let us try to see that what is delta rho by rho scale, that means what is the change in density relative to its original density. So if we do that, it will be half rho u square by k. Remember one thing, that this k by rho, it is something which is a very fundamental quantity which you have studied in physics. What is this? Or square root of k by rho, if it reminds you more. This is fundamentally sonic velocity, sonic speed, so to say. What is sonic speed? Sonic speed is not just speed of sound. Sonic speed is the speed by which a disturbance propagates through a medium, and here we are talking about this type of disturbance through the elastic property of the medium, so it happens to be the speed of sound. Okay, so this is the sonic speed A, so where A we call as sonic speed. This is a very basic high school physics based definition. So keeping this in view, we can write this as half u square by a square. So you can see that the relative change in density is related to a quantity u square by a square. What is this u square by a square? This is a non-dimensional quantity that you can see because it is a ratio of two velocities. So in the numerator you have u, in the denominator you have a. So u is the velocity of flow and a is the velocity of a disturbance which is moving in the medium in which the flow is occurring, and these two ratios is known as Mach number. I mean ratios of these two numbers is known as Mach number. So you have heard about the Mach number, like a jet moving with a Mach of this. So higher the Mach number, higher is the velocity of flow relative to the velocity of the disturbance with which the disturbance propagates within the medium, and therefore we say that it is having a more and more compressible effect. The reason is, if you have if you just write this delta rho by rho, you see that it will scale with half of square of the Mach number. Therefore higher the Mach number, higher is the effect of the change of density relative to its original density. So Mach number therefore is a very important indicator of something which is called as compressibility of a fluid. So what is the signature of compressibility of a fluid? We will say that a fluid is compressible when it has a change in density because of a change in pressure. So in that way all fluids are compressible, right, because all fluids will have some change in density because of change in pressure. But when we say that a fluid is incompressible, what we mean is that that effect is negligibly small. So a compressible fluid and an incompressible fluid, these are just conceptual paradigms, there is no fluid as such which is incompressible, but when we say that a fluid is incompressible, we mean that its compressibility effect is very small. Again, how small or how large, that is something which may be debated. So let us say that we are talking about a change, this relative change, say 5%. So let us say that if we say that this change is less than 5%, we say that it is almost incompressible. So if we want to see that what will lead to that 5%, so one may work it out with, say 5% means 5 divided by 100. So what would be the threshold Mach number for this? Roughly 0.3, right? So 0.33 or whatever, but roughly 0.3. That means if we say that a relative density change less than 5% is something which we do not consider as a compressibility effect, that implicitly means that a Mach number less than 0.3 is something which is not going to give us any serious compressibility effect. So this is important because whenever you are analyzing an engineering flow, nobody will tell you that whether the flow is compressible or incompressible. As an analyzer, it is your responsibility to make a judgment of whether you are going to use the concept of compressible flow or incompressible flow for the analysis of your problem, and then you have to be confident that whether a particular analysis methodology is going to work or not. Of course, for all flows compressible flow and analysis will work because all flows are compressible, but it is like if you have a mosquito, you will not like to kill it with a cannon. So if you are ready or if you are having the possibility of doing a relatively simple analysis, one should not go for a complex analysis. That is what all of us have learnt in engineering, that do not go for unnecessary complication until and unless it is absolutely required. So whenever compressible flow analysis is not required, we should not go for it, and this Mach number of flow will give us a guideline of whether we should go for a compressible analysis or not. A couple of other important points or remarks are there regarding this definition of bulk modulus. One is, see, in this definition we have talked about a change in volume because of a change in pressure, or equivalently a change in density because of a change in pressure. But pressure effect of change of density, it depends on the type of process. All of you have heard of certain thermodynamic processes like adiabatic process, isothermal process and so on. So given a particular system, how the density will change with pressure will depend on the nature of the thermodynamic process. So this definition as such fundamentally is not incorrect but incomplete, because it does not talk about the thermodynamic process by which you are trying to have this change of state. So there are more fundamental or correct definitions of this in terms of specifying it as, say, either a reversible isothermal process, reversible adiabatic process and so on, but we are not going into those details here because thermodynamics is not the scope of this particular course. But we should keep that in mind, because whenever you will be studying thermodynamics, again this type of definition will come into the picture, and there more detailing will be done in terms of whether it is a reversible adiabatic process, reversible isothermal process and so on. So that is one of the important concepts. The second important concept is as follows. Say you are interested to identify whether a flow is incompressible or not, and in that respect there is a subtle difference between the concept of incompressible fluid and incompressible flow. These are very subtle concepts. So when you talk about an incompressible flow, what you mean is that if you have a volume element of a fluid, that volume does not change. So incompressible flow means that there is no volumetric strain of the fluid element, there is no change in volume. But you cannot directly always relate it with this definition, because the change in volume may not always be due to change in pressure directly, it may be because of something else also. I mean, there are reasons for which you might have change in volume of a fluid element not because of the change in density due to change in pressure, but maybe because of change in density due to change in temperature, not directly due to pressure. So, whenever we are talking about incompressible fluid, we are talking about that we are asking ourselves a question that is there a change in density because of a change in pressure. If that answer is that yes, it is significant, we call it a compressible fluid, but not compressible flow definition is something more general. Compressible flow means a fluid element which if it is going to have a volumetric strain or change in volume per unit volume by whatever reasons, it need not be just due to pressure or it may be because of anything, then we say that it is a compressible flow. So, compressible fluid and compressible flow are related because of course one of the reasons of being a fluid compressible or being a flow compressible is because the fluid itself is compressible. So, the density change due to change in pressure is significant, but there could be other effects that are creating the change in volume. So, this is a concept that we should remember. Next what we will do is we will try to learn about a very important property of fluid which is called as viscosity. So, when we talk about viscosity, we will not try to just learn it in abstraction, but we will start with an example. Let us say that you have a flat plate, just like the top of a table, a flat plate, and fluid is coming from far stream, just like say fluid is being blown from that side, it is coming on the top of the table and going away. So, the top of the table may be like a flat plate. So, let us say that the fluid is coming with a uniform velocity from a free stream. In fluid mechanics usually we give such a symbol infinity with a subscript to indicate that it is a free stream condition. So, infinity subscript is like a free stream velocity. So, it is coming with a uniform free stream velocity. Now, that freeness will be disturbed because of the presence of the plate, and let us see that what is going to happen. So, when this fluid first comes in contact with the plate, what happens? Let us first try to understand that say there is a fluid molecule which comes in contact with the plate. So, what will the plate like to do with the fluid molecule? Let us consider two different examples, one is for a gas and another is for a liquid. Usually whenever we discuss about fluids, we are either talking about gases or liquids, but sometimes their physical behavior it is better to discuss distinctly or differently. So, let us say that there is a gas molecule as a first example which is coming falling on this plate. So, what will happen? There will be first a tendency that the gas molecule is adsorbed on the surface. So, once it is adsorbed on the surface, then what will happen, that it will exchange some of its momentum with the surface. So, it will try to have it slowed down, and then again it will try to be getting ejected from the surface. So, it is like a molecule falling on the surface, adsorbed on the surface, getting ejected from the surface like this. So, in this process many molecules are colliding with this and they are exchanging their momentum with the wall. So, if there are very large number of collisions, so to say theoretically infinitely large number of collisions, then this kind of momentum exchange will bring on an average the molecules in equilibrium with the surface. So, if the surface is at rest, the molecules will also be at rest. So, that will imply that there is zero relative velocity between the fluid and the solid at the point of contact, and this is something which is known as no slip boundary condition. So, fundamentally what is the no slip boundary condition? It is 0 relative tangential component of velocity, to be more accurate, 0 relative tangential component of velocity between the fluid and the solid at their points of contact. We are not talking about the normal component because still the molecule may be colliding like it may have a sort of elastic collision. So, it may bounce back, so it may have a normal component. Now obviously regarding the normal component there are issues like if the molecules are sufficiently large in number and they are at the wall, they cannot penetrate and go through the wall, wall is not having holes. So that is called as a no penetration boundary condition, then there even the normal component of velocity will become 0. But no slip boundary condition does not talk about that. That is a separate consideration. No slip boundary condition talks only about the tangential component of velocity. So 0 relative tangential component of velocity between the fluid and the solid at the point of contact. Now as I am telling this to you, you are tending to believe that this is always the correct picture, and this has happened really for a long time. So for a long time this no slip boundary condition was taken as something which is like a ritual which should not change. And the reason was that for many or for most engineering flows it is still valid, or it has been experimentally found to be very accurate. But whenever we are understanding this concept, we should ask ourselves a question: are there conditions in which the no slip boundary condition may be violated? It is important because in many of the modern day applications of fluid mechanics, especially fluid mechanics in small length scales, this boundary condition is something which is put under serious question. So obviously we need to see that, or we need to appreciate that this is just a conceptual paradigm. It is not something which is a ritual and which is expected to work always. Let us see, let us try to look into an example with in the context of gas flow that no slip boundary condition does not work. So let us say that you have gas molecules but not very large number of gas molecules. So then what will happen? The molecules will be exchanging momentum with the wall, but there will not be very large number of collisions. Because there will not be very large number of collisions, the momentum exchange will not be complete. So there will be some velocity of the fluid relative to the solid boundary, even if otherwise we tend to believe that there should not be any slip. So that is just because of the rarefied nature of the medium, that there is not sufficiently large number of molecules to have a theoretically large number of or infinite number of collisions. On the top of that, there may be local strong gradients in density and temperature, and that might itself induce motion of molecules of gases over the solid surface. So these are called as phoretic motions. If these are induced by temperature, these are called as thermophoresis, and these may be induced by any other effect, but temperature is one of the common effects by which, by introducing a very high gradient of temperature, you can introduce local flow of molecules of gases over the solid boundary. So we can see that there may be situations, and there are likely to be such situations when the no slip boundary condition is not valid, but well, in most of the engineering systems that we are talking about, the no slip boundary condition will work for gases, except for rarefied gases or maybe gases which are not having sufficiently large number of molecules, or gases being subjected to very high local gradients of density or temperature. For liquids, it is difficult to believe that the no slip boundary condition will not work, because liquids are very compact systems. So liquid molecules will not be insufficient in number to have inadequate collisions with the wall, but for liquid molecules there may be slip because of certain reasons. So to understand the picture of what happens in the liquid molecules, let us consider a small element of surface like this. The surface may look very smooth on the top, but if you look it into a very powerful microscope, it will be much worse than what I have drawn here. So it will have lots of peaks and valleys, and what will happen is that the molecules will nicely sit on these peaks and valleys. So some will be entrapped like this, and because of a compact nature, what will happen, whatever is entrapped is not easily being escaped, and that will make us believe that yes, it will be a no slip boundary condition. At the same time, if you are having a very high shear rate which is being introduced on the liquid, say a very high rate of shear strain, what will that try to do? That will try to forcefully dig this out from or take this out from these locations. So then in that kind of a context, the liquid molecules may also slip on the surfaces. Otherwise, if you have very smooth surfaces, say you must have heard about carbon nanotubes. These days those are very sophisticated and fascinated technologies to produce carbon nanotubes. So those are very smooth tubes, and if you are having liquids in contact with them, now obviously there will be the van der Waals forces of interaction between the surface and the liquids, but if in such case water flowing through those nanotubes will have very ordered hydrogen bonding, and then the motion of that water will be such that it can overcome the van der Waals forces of interactions. Those are relatively weak in comparison to this strong bonding in the water, to overcome the wall attraction and flow on the top of such surface. So it may actually slip, and these are called as highly slipping surfaces. Therefore, we have to keep in mind that no slip boundary condition is a paradigm which will work for most of the engineering problems that we are going to consider, but at the same time we should not take it as a ritual. We should keep in mind that there are situations in which it might be violated, but for practical purposes, for almost all the problems that we are going to solve in this particular course, no slip boundary condition will work. Okay, so let us stop here today, and in the next class we will take this up and introduce the concept of viscosity through this no slip boundary condition that we have discussed today. Thank you.